Okay, so the first thing we need to talk about is something called Riemann Sums. All right, and before we do that, let's just discuss real quick. I hope you guys have paper and pencil over there to write some stuff down here, because I'm going to teach you a little bit of new stuff very quickly. So first off, before we go into all of this, let's make sure we all remember what the integral is saying, okay? The integral from a to b of f of x dx is asking us two things, okay? They're both equal to each other. It's asking us to find the signed area between f of x and the x-axis, and it's also asking us to find the change in the antiderivative of f of x on a to b. And we spent a lot of time doing that before we left school. But don't forget that's going to be important for the AP test and just for future math classes if you end up using calculus anywhere. So we are going to exploit that. I'm going to make up a super simple example and show you how we handle that from a table. Okay, so on the AP test and in real life sometimes you just have like a table of data. A lot of times they give it to you like this, where they'll give you like x's. I'm just making up some random x values here. And we'll go to 8 maybe. All right, so those are some x values we happen to know. The y value is 4, and we'll say we know this is 2, 7, 5, 1, and I don't know, 3. Okay. That looks good. So again, that's the same thing, kids, just so we're not confused, as like an XY chart, having like 0, 2, 1, 7, 3, 5. All right, they just always give it to you as a horizontal table there. That's all. Cool. So we don't know what f of x is like explicitly. We just have a few points on there, and a couple things they're going to ask you to do. Number one is they're going to ask you to use IVT. Okay, if you remember what that means. For instance, they might say, is there a place where f of c has to equal like 6? And we're going to say, yes, definitely. And we're going to use IVT for this because they're also going to tell us up here somewhere in like a prompt, hey, by the way, f of x is either continuous or it's differentiable. They'll tell us one of those things if they're going to ask this question. Okay, but we're going to say, yes, it has to equal 6 because if we graph it, which you don't have to graph it, but if you graph it, we know it's going from 0, 2 to 1, 7 to 3, 5. So 2, 3, 5 would be like right here. 4, 5, 6, 1. So again, I'm just plotting all these dumb points, and then 7, 8, 3. All right, so obviously 6 is going to be like right around here, and you can see since it's continuous, it has to go through 6. To get from there, it has to go through 6 once, and it's got to go through 6 again. All right, so let me switch up colors here for a second. So just because we have these points doesn't mean we know exactly what this curve looks like. It's possible this curve is a nice, simple, easy curve like this. All right, that's one possibility. It goes through all those points, but it's also possible that this curve is crazy. Oh, I don't want to do all that. Okay. That this curve is just absolutely insane and does all kinds of weird stuff. Like it could go way down here and then come way up here and then go through that point there and then do all this junk. I mean, the curve could be super insane. So keep that in mind. All right, so just because you don't see like f of x hitting any negative values on the table doesn't mean it doesn't hit negative values. Okay, but what we do know is true is, and we can write this like this, since f of 0 equals 2, which is less than 6, which is less than 7, which is f of 1. We're basically saying, yeah, it goes from 2 to 7, so it has to go through 6. Then f of x must equal 6 at least once by IVT, since f of x is differentiable. I should have typed this out, it'd be a whole lot neater, but since it's differentiable and thus, saying thus is always fun, thus continuous. Okay, so notice I'm not saying it, I'm saying f of x, like don't say the graph, don't say the table, name the function. That's the basic idea for IVT. All right, okay. I imagine you're all doing very well. We'll talk about the second thing they're going to ask you to do is like they'll use MVT. Actually, yeah. Okay, let's just go with MVT. They'll say, must there be a place where the derivative equals a specific value? And we're just going to go, let me see, over 8, so 1/8. So they'll say, must the derivative equal 1/8 somewhere? And that's MVT. And what MVT tells us is whatever the average rate of change is, and if we take the average rate of change from 0 to 8, that would be f of 8 minus f of 0. And they always set us up like this. They usually make it pretty simple. Over 8 minus 0. So that's the average rate of change, which equals 3 minus 2 over 8. And that's just from the table up there. And that happens to equal 1/8. All right, and I'm going to use my keyboard for this since my handwriting is relatively atrocious. All right, we're going to say, since the average rate of change of f of x on 0 to 8, so on that interval, is 1/8, then by MVT, f prime of x must equal 1/8 at least once, since f of x is continuous, is differentiable, and thus also continuous. All right. So those are pretty basic questions from a table you should be seeing as we go through these free response questions. I'm going to copy this table down here so that I can keep going through this stuff. Yeah, give me the table. Come on, copy. Chaboom. All right, so another thing they might ask you to do here, and this kind of ties in with MVT a little bit, is just approximate f prime of 2. All right, now f of 2 would be in here somewhere. We don't have that value, okay? Like from my graph, which I graphed way up here, and I will also steal, just so I don't have to draw it again. Again, you don't have to draw this graph, but it helps if you're a little stuck. Now, you're not going to have a ton of time on this AP test, okay? But when they give you a bunch of points, all they're really doing is giving you a graph. So again, we know it looks like that. Again, f of 2 would be somewhere along this line. I don't know what it is. It could be any value at all, honestly. But the way you approximate any derivative from a table, always and forever, is you just find the average rate of change. You find the slope on the interval where that x value is. So the x value 2 is between 1 and 3. So all you need to do for this, it's not much work at all. You don't need to explain anything. You're going to say f prime of 2 is approximately f of 3 minus f of 1 over 3 minus 1, which is 5 minus 7 over 3 minus 1, which is negative 2 over 2, which is negative 1. That's how you approximate a derivative from a table. Okay, and all you're really doing is you're finding the slope of there. So all we're saying is the curve goes through there. The derivative of 2 should be something along those lines. That's the best we can say about it. It's possible that it's way, way, way off, but that's the best that we can say. All right, and then the last thing they're going to ask us to do, which is the most fun, is to approximate an integral from this chart. And we are going to use the fact that, and let me steal this thing again. Oh, let me erase all this. I should have copied this out twice, but whatever. All right, so we're going to exploit the fact that the integral is just the area under this curve, and we're going to use a little bit of geometry to approximate this integral, okay? So I'll paste it once there. I'll paste it once down here. We'll use this graph a couple times, and I'll paste it once down here. Okay, so same graph there. All right, so they'll say these words. So this is the fourth thing from a table you can expect to be asked to do. Approximate the integral from 0 to 8 of f of x dx. Now, when they ask you for a derivative, they're just going to say approximate the derivative. They're not going to tell you how to do it. They're just going to say, boom, approximate it. You always just find the average rate of change. All right, let me check our messages here. Nobody's saying anything? Everybody's good? Okay, great. All right, so if they ask you to approximate an integral, however, we're going to have 4 ways that we can do this, and it's not up to you to decide. They're going to tell you which way to do it. So we're going to do this 4 different ways for you. Okay, so approximate this integral with, and they'll say something like a right Riemann sum. I'm just going to call it an RS. A right Riemann sum, or a left Riemann sum, or a trapezoid rule, or with a mid Riemann sum, or with a midpoint rule, something like that. Okay, so we're going to have a right, we're going to have a left, we're going to have a midpoint we're going to have to talk about, and we're going to have a trapezoid rule. all three of these, mid, right, and left, we're going to use rectangles. Okay, and I'm going to show you that real quick. It's not very difficult. Once you see it, it makes some good sense. Trapezoid rule, we're going to use trapezoids. Okay, so I'm going to erase all that so we can have a little room here. But again, they're going to say write Riemann sum. And I'm not entirely sure. I always misspell Riemann. I'll probably misspell it here. It might be EI. I don't know. Riemann some guy. He's going to be offended that I'm spelling his name wrong. But luckily, he's not here anymore. So, with a write Riemann sum. Here's what that means. It means you're going to chop up. Oh, they'll also tell you. So we have all this. So the whole interval goes from 0 to 8. But we have an interval from 0 to 1, from 1 to 3, from 3 to 6, from 6 to 8. So they'll say with 4 subintervals. And they'll always give you the right number of subintervals. I'm not going to mess with you. So we have 4 subintervals on this table. That means we're going to chop up the interval from 0 to 8 into 4 subintervals. Now, it makes sense if you're thinking about this. If we're going from 0 to 8 in 4 steps, we could do 0 to 2, 2 to 4, 4 to 6, like chop them up into 2s. But if you have a table, you have to use the values you're given. So our first interval has to be from 0 to 1. Because those are the x values I know. I know x goes from 0 to 1. So I have to use those because I also need the y values. So I have to use the x values for which I know the y values. But the whole idea here is we're going to write this integral from 0 to 8 f of x dx is approximately equal to, and I'm going to go from 0 to 1 and put a rectangle in there. So the left side goes up to 2 because that's the y value at 0, and the right side goes up to 7. What the right Riemann sum does is it makes a rectangle in there with the height of the right-hand y value. So the right-hand y value, if you know your left from right, is 7 in that interval. So we're going to make a rectangle in here that looks like that. So let me just go ahead and sketch what the simple curve could look like. Remember, it's going through these points. So this curve could look something simple like this. And we're trying to find the area underneath of it, technically. All right, so the first thing we're going to do is put this blue rectangle in there to represent the area under the green. Now, it's not a great representation, right? It's definitely an overestimate up there. Okay, but let's not worry about that yet. That doesn't matter. It doesn't matter how good it is or not. You're just asked, can you do it? So our first rectangle has a base of 1 and a height of 7. And again, 7's coming from the right-hand side of this interval, right there off that table. My next rectangle goes from 1 to 3. It's going to have a base of 2. You're going to see it right here, from 1 all the way to 3. So that'd be in here. Now there's 2 sides to this, right? There's the 7 side from 1 to 3, and there's the 5 side. We're going to use the height at 5, because that's the right-hand side. So that rectangle has a base of 2 and a height of 5. All right, and notice the base, even though we're going from 1 to 3, right? The base isn't 3. The base is the distance between 1 and 3. So it's just 2 times 5. And all we're doing, again, is putting 4 rectangles under this curve and saying that approximates the area. Plus, my next rectangle goes from 3 all the way to 6. So it's going to have a base of 3 and a height on the right-hand side of 1. And again, that does not look great for an approximation of that area, but that's the best we can do. Plus, my next rectangle is going to go from 6 to 8. So that's got a base of 2 right here, and it's going to have a height of 3. So it's going to look like that. All right, and you can add that all up if you want. That's just 1726. All right, but on the free response section, you can honestly just leave your answer like this. You don't even have to simplify it. Okay, so keep that in mind. If you're running out of time or you're not sure how much time you have and you have just arithmetic left to simplify for your answer, don't worry about simplifying it. All right, so if they had asked us to do a left Riemann sum or a left-hand sum, then we would do it like this, the integral from 0 to 8 f of x. They're not going to ask you to do all of these. They're going to ask you to do one of these. I'm just running through them all so you can see the difference. Okay, so the integral from 0 to 8 f of x dx for a left Riemann sum, my first rectangle, you can see it right here, still has a base of 1. Nothing stopping that. The base is still 1, but now I'm taking the height on the left side. That's a height of 2. Plus, my next rectangle has a base of 2 still, but the height on the left side is now, that's 7. So it looks like that. Plus, My next rectangle has a base of 3 because we're going from 3 to 6, and it's going to have a height of 5. So the base is 3, the height is 5. Plus, my next rectangle has a base of 2, but it has a height of 1 now. So 2 times 1. You can add that all up, or again, you can leave it like that. All right. For midpoint sum, instead of taking the height from the left or the right, you'd actually take the height in the middle of the interval. Now, to do that, though, you need a table that's going to cooperate. For instance, if I wanted to go from 0 to 1 and take the height in the middle, I would need to know the height at a half. Well, I don't know the height at a half, so I can't do that. All right. So this table is not set up for us to do a midpoint sum. They won't ask it from a table like this. So I'll make up another table real quick, and then I'll go back up and do trapezoid rule for the old one. But if they ask us to do a midpoint sum, they'd have to give us a table like this. 0, 3, 6, 9, 12. All right, and I'm just going to put some numbers in here. These are just made up. All right, and they'll say approximate this integral with a midpoint sum, and now they're going to say 2 subintervals. So that means they only want us to use 2 rectangles instead of 4. And the reason that is because of this. We're going to go from 0 to 6 as 1 rectangle, and we're going to take the height in the middle, which is at 3, which is going to be 4. Our next rectangle is going to go from 6 to 12, and we're going to take the height in the middle, which is at 9, and that height is 8. So we'd write this integral from 0 to 12 of f of x dx is approximately equal to, and my first rectangle has a base of 6 and a height of 4, because I'm taking the height in the middle, plus my next rectangle has a base of 6 and a height of 8, because I'm taking the height at 9, which is between 6 and 12, right in the middle. All right, and that's going to equal, what, 24 plus 48? I don't know, what is that? 72? 72. Hopefully that's right. Okay. Yeah, 6 times 12. Okay. All right, so that's that. So those are the 3 rectangle ways they'll ask you to do it. And the last way they'll ask you to do it is they'll say, hey, approximate it using the trapezoid rule. And that's a fancy name for using trapezoids to find the area. So check this out. Let me sketch this in red just so the curve is different. So if the curve, again, simply looked like this, which it could look crazier, but let's make it as simple as possible. What we're going to do is we're going to put trapezoids in here. So on our first interval, which goes from 0 to 1, rather than taking a height and just going straight across and making a rectangle, we're going to connect these two like that. And that makes a trapezoid. All right, so let's talk about trapezoids for a hot second, because sometimes kids don't like them very much, but they're pretty sweet. A trapezoid has a height, it has a base 1 and a base 2. And the area of a trapezoid is 1/2 the height. It's just like a triangle. It's half the height, but you got to add the bases. Base 1 plus base 2. All right. Now, the reason why I'm drawing that over here is because our trapezoids, when we do the trapezoid rule, aren't going to look like that. They're going to be turned sideways. So I'll make sure everyone's on the same page here. This is still the height. The height is the distance between the bases. Okay. So the height is actually the change in the x values. It's how big the interval is. And the bases are actually the y values. Okay, that's just how far up the bases go. So over here, when we do trapezoid rule, because I have 4 subintervals, right, and that's just a consequence of my table, remember? 0 to 1, 1 to 3, 3 to 6, 6 to 8. We're going to have 4 trapezoids, just like the left-hand sum and the right-hand sum had 4 rectangles. So my first trapezoid, so again, you're going to write the integral from 0 to 8 of f of x dx is approximately, every one of these trapezoids starts out with a half times the height. The height of my first trapezoid is 1, because that's how far apart the bases are. The bases of my first trapezoid are 2 and 7. That's the first trapezoid. Plus, we're going to take the second trapezoid. Well, that's going from 1 to 3. So that has a height of 2. And the bases are 7 plus 5. That's my second trapezoid. And you can see the trapezoids do a much better job approximating the area under that curve. Plus, 1/2 times the height of the next one goes from 3 to 6, so that's a height of 3, and the bases are going to be 5 and 1. So 5 plus 1 plus 1/2 times the next trapezoid has a base of 2, or height of 2, I mean, and the bases are 1 and 3. So that's that. And again, you can add that all up, but on the AP test, I would honestly just leave it like that. Because this is weird. If you leave it like this and it's correct, you get full credit for that, right? If you simplify it and mess up and you're off by like 1 or something like that, you don't get credit for the answer, which is crazy. So don't really pay too much attention to simplifying things as long as it's all like arithmetic easy stuff. If it's an equation you're supposed to solve, you got to solve that. If there's trig and stuff in it, you should probably simplify that. But arithmetic and multiplication, addition, subtraction, just leave it the way it is. Okay, so that's my spiel on Riemann sums. We would usually take like a whole week and go through this. And there's a little bit more I got to talk about, but we'll do that later on. But the basic idea is what we just did there, okay? So you're going to have, from a table, they'll ask you about IVT, they'll ask you about MVT. We've talked about those. Okay, you're going to see them pop up in the free response questions. Just look at the answers, look how they're written. If you have any questions, let me know. They're going to ask you to approximate a derivative. That's just the average rate of change. You should hope to see that question because it's super duper simple. And then they're going to ask you to approximate an integral, which they could do one of 4 ways. A right Riemann sum, a left Riemann sum, and a trapezoid rule, right? And if it's a midpoint rule, just remember, you've got to skip over one of your numbers because you have to take the height in the middle. All right, so let me come, whoa there, Chief, way up to this thing. We might have to talk about 4 here, but I don't want to do that yet. I want to talk about this right here in particular, okay? So just make sure we're okay with this. So this is question 4 from 2018. Well, that's for this week. Let's talk about the 2019 ones first. The 2 that I pulled out of 2019 are 4 and 6, okay? So if you have other questions, let me know, and we can go over those. But I just want to talk about, so this is a totally separate topic from Riemann sums, okay? This question is all about differential equations. All right, and all a differential equation is an equation that has a derivative in it. So this right here is a differential equation. All right, and all they're telling you is the rate of change of h with respect to time is equal to this formula, -1/10 the square root of h. So let me give you a super duper 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 simple related or differential equations question. Here we go. Boom. dy dx equals 2x. Okay. I want you to notice something here that's different than what they did in the question they asked you, okay? My top variable is y. That is the dependent variable. My bottom variable is x here in the derivative. That's my independent variable, all right? Notice over here in my derivative, I've given you the independent, I'm giving you x. So obviously, if dy dx is 2x, everybody knows that y has to be an x squared, right? But technically, there's an x squared plus c. There's some number at the end, true? So the solution to a differential equation is just what is y, or the dependent variable, such that when you derive it, you get this derivative, okay? So that's the solution to this simple little blue differential equation. Now, what we're really doing there, even though we're kind of skipping over a step here, is this. We're actually moving that dx over with the 2x. That's really what's happening there. So we're going from this box here, dy dx equals 2x, to this over here, except we're kind of doing it all in our head. Because then what we're doing is we're actually integrating both sides of this. And the integral of 1, there's a 1 in here in front of this dy. The integral of 1 dy is an x. That's the integral of 1 dx. The integral of 1 dy is y. And technically there's a plus c on that y, but we don't put it on the y side. We only put it on the x side. The integral of 2x is x squared plus c. Okay, and this is called, oops, the general solution to the differential equation, okay? It's called the general solution because there's a c in it. Like, we don't know what c is. We don't have an exact function. If they had told us, let me slide over here a little. Oh, by the way, dy dx has to be 2x, and it has to go through the point 0, 6. Well, now we know y has to be x squared plus c. But since it has to go through this point right now, which I just made up completely arbitrarily, when I plug in 0, I have to give 6 back for y. So the function I'm actually looking for, the equation I'm actually looking for is that. And this is called the particular solution. So they might ask you to find the general solution. All that means is you don't have a point to plug in and you're not going to be able to find out what C is. Or they could ask you to find the particular solution, which means find the general solution and then use the point you were given to find C. Okay? Now, something we haven't talked about yet, though, is over here. Let's go way back here. Is this derivative they've given us, the variable that's over here is this h. And that's the variable that's in the numerator over here. That's our dependent variable, which is different than the easy example I gave you up here. So what you need to pay attention to now when you're given a derivative is where the variables are, okay? So when you see that, you don't need to solve this until part C, and that's what I'm going for. So it tells you at 0 seconds, the height is 5. Use separation of variables to find an expression for h is really them saying, hey, solve the differential equation. Find out what h is, okay? But let me show you something. The first thing you're going to do is you're going to move this dt over here. But here's our problem. We can't integrate an h with a dt on it. It's not going to work out. So what separation of variables is a super fancy name for exactly what we're going to do. We're going to move all the h's on the one side and all the t's onto the other side, okay? So we move the dt over here always because we need dt to be in the numerator because we're going to integrate. Like every integral you've ever seen us do has had some x's in it with a dx at the end, right? Or if it had an h here, it had a dh at the end, right, on top. So that's what we need to get these integrals to look like before we can handle them. So I can't handle an h over on this right-hand side. So what I'm going to do is divide by root h. I'm going to leave the 10 over here. I don't care about this stupid 10. And the dt is over here. So what I've just done right there, okay, I've taken the differential equation they gave me, which is relatively simple, and I've separated the variables, okay? And all this really becomes then is 2 integrals for the price of 1. How lucky. We're going to integrate both of them, but we're going to rewrite them so they're in the right form. So we need the integral. This is h to the negative 1/2 power dh is what that really is. And this is just, okay, how'd that just happen there? Whoa there, computer screen. Negative 1/10 the integral of 1 dt is really what's going on there. And again, I'm answering part C here. All right, and then you just evaluate each integral. So the integral of h to the negative 1/2 is h to the positive 1/2 times 2 equals, and we don't put a plus c on the dependent variable side, okay? We just need 1 plus c, and we always put it on the independent side. This becomes negative 1/10 t plus c. And we want to know what h is, so I'm going to go ahead and divide by 2 to get h to the 1/2 by itself. That makes this become negative 1/20 t plus 1/2 c. And then I'm going to square both sides. So h is negative 1/20 t plus 1/2 c squared. Okay, the problem is they told us that at time 0, so we're done. We just got to find out what c is basically. The water should be 5 feet deep, which means when you put 0 in for time, you have to get 5 back for a height. Well, when you put 0 in for time, this boils all the way down to 1/2 c squared, right? So we take the square root and we multiply it by 2. So c is 2 root 5. Remember, okay, right? Square root of 5, boom, 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 times 2. Yeah, it looks good. So c is 2 root 5. And if you put 2 root 5 in here for c, you get 1/2 times 2 root 5, which is just root 5. So this is our answer, and you can double check it a couple ways. I'm going to show you. You can derive it, first off. Actually, maybe, yeah, so I'll show you that. So we can derive it and make sure that we get the right derivative, which is this right here. So let's do that. But the easier way to check it too is plug 0 back in and make sure you get 5. So when you put a 0 into there, you get root 5 squared, which is 5. Okay. The reason why we know this is the answer to our differential equation, check this out. If I derive that box right there, let's drop this up here. We get that dh dt is, all this is one big thing squared. So we got to derive that by doing the power rule. So we get negative 1 over 20t plus root 5. It's not squared anymore, and we multiply that by the derivative of the inside, which is that. Okay? Now, this, ooh, what's up? Oh, Spencer. Okay. All right, so we're multiplying this junk here. The 2 and the negative 1 over 20 just become negative 1/10. Okay, so check this out. Negative 1/10. And we have this whole thing. So that's our derivative, which doesn't look like what they said the derivative should be, right? They said the derivative should be negative 1/10 times root h. But remember what h is. Negative 1/10 root h is negative 1/10 the square root of negative 1 over 20t plus root 5, and h was that squared. Remember that? That's what h was over there. So if you put that into that derivative, negative 1/10 root h, when you take the square root of that thing, you get the answer we got right here. So the same thing. They're just messing around with the variables a little bit. Okay? So that's our lesson for differential equations for the day. And again, we would have taken a whole week or more to go. Differential equations is a super deep topic. For the AP test, you're not going to go crazy on it. There's still a couple things we got to talk about with it, which I will talk about later. But that's the basic idea there. And I want to show you here real quick too. When they give you a differential equation question, which I highly expect them to, they only ask you to solve it usually in the last part. The other two parts are just, hey, do you understand what the derivative is doing? So like question A says, find the rate of change of the volume of the water in the barrel with respect to time when the height is 4. Well, the volume in the barrel is this, right? And we know that the diameter is 2, so that means the radius has to be 1, right? Well, and that's not changing. Remember we did cone-related rates question? This is a related rates question. We did cone-related rates questions where as the height gets deeper, the radius gets bigger, so we had to worry about that. But with the cylinder, super easy. The radius is just 1. So the volume of this thing is really just pi times 1 squared times h. All right, so when they say find the rate of change of the volume, that just means derive volume. That means dv dt is pi times the derivative of h, dh dt. So the way they get students on questions like this is kids will derive that and get like v prime equals just pi times 1 because they'll derive h and get 1. But the problem with that is you're deriving v at that point with respect to h. So keep that in mind because you're getting dh over dh. All right, so pay attention to not just the variables that are in the equation, but what you're deriving with respect to. Many times you do derive with respect to the variable that's independent. But when they ask you how fast is something changing with respect to time, you got to derive with respect to time. And that means every variable has a derivative. Cool. Unless you derive time, then it just becomes 1, right? So, but anyway, you got to do it like that. We want to know what dv dt is. Here's pi. We just need to know what dh dt is, right? That's what we're missing when the height is 4. Well, it turns out dh dt is given to us right freaking here. It's just that formula. And we know it's at the time the height is 4. So if you drop a 4 into there, you get negative 1/10 times root 4, which is a 2. So you get negative 2/10, which is negative 1/5. That's all they're doing. So the difficulty in these questions is not that the calculus is crazy hard. It's that kids mess up what variables they're working with. All right. Then the more you practice that, you're going to see that. Just when you read these, read carefully, pay attention to what variables they're giving you. All right. All right. And then B, when they say the height is 3, the rate of change of the height of water with respect to time, is that increasing or decreasing? They want to know the second derivative of that. So you can look up the answer to that. I hope you've already done that. I'm not going to go through that because I want to talk about question 6 from last week as well. Because I want to talk about the L'Hopital's rule thing here, okay? But first off, let's just go through this whole thing. They're telling me, and I really expect them to do something like this year too, because they're not just going to give you straight up, like, can you derive functions that we were deriving in class, right? They're going to make up weird questions like this to make sure, like, do you understand what the derivative is, how to find it, but also they just want you plugging stuff in online. So they're telling me that f, g, and h are all three functions that are all twice differentiable, which means we can find their derivatives and their second derivatives everywhere. And the only thing we know about them is that g of 2 and h of 2 are both 4, and this is the tangent line to both of them. All right, now they move that 4 over on the other side here, but the way we usually write this is this: y minus 4 equals 2/3 x minus 2. And the reason why that's a tangent line is because we know it goes through the point 2, 4, so that's why it's y minus the y value, x minus the x value, and the only thing you're missing is the slope of the tangent line, but that's just the derivative at the x value. You found it, so that's just h prime of 2. So h prime of 2 has to just be 2/3. That's it. Okay? That's just because it gave us the tangent line. Nothing even sneaky about that. Question B, I'm probably going to go over an hour here, kids. You can dip out if you want, but I'm going to finish this whole question here, okay? Question B is saying, what's the derivative of that? And that's just asking, hey, do you know the product rule, basically, right? So a prime of x, derive the first thing, right? That's just 9x squared times h plus, shut up you, leave the first thing, derive the second thing. That's it. When you derive a function h and you don't know what it is, it's just h prime. And then to find a prime of 2, just plug that junk in. When you put a 2 into there, you get 4 times 9, that's 36. Right? That seems right, yeah. Times h of 2. Well, they told us h of 2 was 4. Boom. Plus, right? They told us that right up here. Plus 3 times 2 cubed is an 8 times h prime of 2, which they made us find up here. Okay? And remember, let's say you weren't sure how to find h prime of 2, and they asked you to do it up in part A. You could write, make it up, put something up here so that you can use it here. It doesn't matter if it's wrong in A. I mean, like, you won't get the points for A, but you will get the points for B if you use that wrong answer in B. Like, they don't mark you wrong twice. Okay? They know that you're supposed to use whatever you said h prime of 2 was here. So even if your h prime of 2 is wrong, if you're using the same number you put up here, you still get full credit for part B. All right, let's talk about C. Here's what L'Hopital's rule says, okay? And they're kind of making us do it backwards here. So let me slide over here. Let's talk about L'Hopital's rule. So here it is, ready? It's this. If the limit as x goes to a of some function is 0. So basically, if you plug in a, you get 0 for f. And the limit as x goes to a of g of x is also 0. Then, if we happen to be trying to evaluate the limit of their quotient, that's a fancy word for fraction there, calculus kids. So, if you try to plug in a into here, right, f of a is going to become 0. So this is technically going to give us back 0 over 0, right? But you don't write that. Don't write that there, because 0 over 0 is not a thing to say it's equal to. Okay? What L'Hopital's rule says is it happens to be equal to the limit as we approach a of just their derivatives. So we can derive the top and the bottom, not with the quotient rule. We can just derive the top, derive the bottom, and we plug a in. That'll be the same answer. Let me show you a very, very stupid, simple example. One of the very first limits we did in the very beginning of the year was this. Okay? And we talked all about that. We talked an awful lot about limits back at the beginning of the year. And when you put a 2 into there, you get 0 over 0, right? Everybody sees that. Okay? So what I had you do, because we didn't understand derivatives at the time, I told you if you get 0 over 0, that means, yo, something has to cancel out. It has to. If it's all algebra, like factoring and multiplication. If it's exponential or logs or trig, that's not the case anymore. But all we ever saw here was all just like algebra and roots and stuff. But either way, the top and bottom factor, right, this cancels, and you also get back 4 as your answer. Okay? So that's how we handled. That was not using L'Hopital's rule. I'm going to show you how to use L'Hopital's rule right now. All right? We would write this. First off, now again, you want to use L'Hopital's rule for this because it's just stupid easy to factor and cancel, I guess, right? You can still use L'Hopital's rule. It still works. It doesn't matter. But first you notice is if I put a 2 into there, I get 0 over 0, okay? which means I can use L'Hopital's rule, but on the AP test, you have to explain that. So you write this, since, notice I'm not writing equals 0 over 0. Don't do that. This is super wordy. You only got to do it once, but you got to show the limit of the numerator is 0 and the limit of the denominator is 0. So since those two things are true, hooray, I can use L'Hopital's rule. It's like the hospital, right? I can use L'Hopital's rule. So then you write, let's zoom out a little so we can see the whole thing. It becomes the limit as x approaches 2 of the derivative of the numerator over the derivative of the denominator. And when you put a 2 into there, you get 4, which is the same freaking answer we got down here. All right. The problem is, not the problem, this is all cake. The problem with some questions is sometimes you can't factor and cancel. Sometimes they're too hard to do that, but L'Hopital's rule still works. And it's just a very easy example of that could be this. All right. When you plug a 0 into there, you do get 0 over 0. But because there's an exponential thing, it doesn't factor. Like there's no way to cancel that out. But because we get 0 over 0, you could write, since the limit as x goes to 0 of e to the x minus 1 is 0, and the limit as x goes to 0 of x is 0, dot, 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 I can use L'Hopital's rule. Cool, so you got to write all that junk out, and you derive the top, boom, e to the x, derive the bottom, 1, and now when you put 0 into there, you get 1 over 1, which is 1. So that limit must equal 1, okay? Which, keep in mind, that means if you were to graph it at 0, it looks like that. There's a hole there. Both sides are going to 1, but there's a hole there. All right? Okay, so let's come all the way back to the question at hand, which was this thing. And they asked this kind of weird. All right, they say here, ready? This function, h, which has an f in it, that's great. It's known that this limit can be evaluated using L'Hopital's rule, okay? And that tells us this, that if I try to plug a 2 into the numerator, it had better become a 0, and it does. And that means if I plug a 2 into the denominator, it's also going to become a 0, okay? Now, I don't know that because I got the dumb f of x there, but that has to happen because they're saying you can use L'Hopital's rule, all right? And that's something we'd have to write down here. Since we can use L'Hopital's rule. So sometimes the S is in there, sometimes there's not. I go back and forth. The limit as I approach 2 of the denominator must be 0. That has to happen. That's the only time you can use L'Hopital's rule, if you get 0 over 0. So that limit has to be 0. All right? Which means that 1 minus, when you evaluate a limit, you just plug into the thing, right? That has to be 0. Which means f of 2 cubed had better be 1, which means f of 2 is just 1. That's the first part of the question. They say, hey, find f of 2. That's it. Okay, and that's all based on the fact that L'Hopital's rule can be used. The second thing now, because they want us to find f prime of 2, the second thing we need to do is notice that several things are happening here, okay? So again, you got to read everything they're telling us. So let's talk about this. H, all the functions are twice differentiable, okay? That means is they are continuous and you can find their derivatives, okay? So remember our definition of continuity was this. If a function was continuous at 2, then if you took the limit as you approach 2, you had to get back the same y value. And we talked a good bit about that back in like September, October, okay? That right there is our definition of continuity. If they ever ask you to show something's continuous, that's why it's continuous, because as you approach 2, you just get the y value you're supposed to get, all right? Now, the fact that when I put 2 into this function and get back 0 divided by 0, that's why they have to put this here. Hey, that rule doesn't work at 2. This is like a piecewise function kind of for h of x, which is a little bit weird. But here's what I know. If I take this limit, I have to get back what h of 2 is. And they told us that h of 2 is 4. Okay? So when we take the limit for h of x approaching 2, put all this together, which should be this, over 1 minus f of x cubed, that has to equal 4, right? But when you put 2 into that, you get 0 over 0, which means we could do L'Hopital's rule. So when you do L'Hopital's rule, which you don't need to explain in this particular question because they told us you could use L'Hopital's rule, you derive the top, that's just that. You derive the bottom, that 1 derives to a 0, and negative f of x cubed derives to negative 3. The derivative of anything cubed is that squared times the derivative of the inside. So that's after using L'Hopital's rule, and this has to equal 4 because that's what h of 2 is. And when you put a 2 into there, you get 4 over, I'm just evaluating the limit part of it now, negative 3 times f of 2 squared times f prime of 2. That has to equal 4. What that really means is that denominator, negative 3 times f of 2 squared times f prime of 2, it better be 1. And remember, we already found f of 2. F of 2 is just 1. So it's negative 3 times 1 squared times f prime of 2 has to equal 1. And when you simplify that out, you scroll way too far down the page, you get that f prime of 2 has to be negative a third. All right, so that's a tricky question. But no, it's like all the math we did wasn't super difficult. It's like the difficulty in these questions always is, what the crap am I supposed to do with what they're giving me here? All right, I'm not going to talk about part D because it's like they use the squeeze theorem in there, and I don't think that's going to be a big deal. Maybe we'll come back to it later on. We got a little bit of time still before the AP test. And if you're still with me, let's check. Let's check our grid view. Oh, a lot of kids are still here. Okay. I'm going to talk about, so for 2018, this week, I actually do this one question, and there's something in here called a slope field. All right. So B and C, you should be okay to handle at this point. Look up the answers. Again, ask questions in that discussion board. But 2018, question 6, they give you this weird thing, which is a slope field. Okay. This last thing we'll talk about will be done by 10 o'clock. You will notice that they're giving you a differential equation right here. You'll also notice that there's an x over here and a y, which means if they ask you to solve this, which they do in part C, you're going to have to move the y's over here. You got to do it by multiplication, right? You're going to divide that whole y minus 2 squared. It's okay to take the whole thing over. Equals 1/3 x dx, and then you're going to integrate both sides. That's how you're going to solve that, okay? Now, part A does not ask us to solve it, though. They say, hey, here's a dumb slope field. Here's what a slope field is, okay? The derivative simply tells me the slope of a function. That's it, okay? But if you know the derivative, you don't necessarily know what points your function goes through, okay? So what you can do is you can hypothesize what points it might go through. For instance, if y happens to go through the point 1, 1, which is right here, see that? Then the slope of it would be 1/3 times 1 times 1 minus 2 squared, right? Because I plugged in 1 for x, 1 for y. And that boils all the way down to 1/3. So that means if my curve goes through the point 1, 1, then the slope there would have to be 1/3 when it does it. So we go to 1, 1 and see we put a little dash there that has a slope of 1/3. Okay, now it's not your job to like measure that out and make sure it's 1/3, but it is 1/3. Trust me. We can do that for any single point on this entire curve. Okay, so what they did was they had a computer go every 1/3. You can see what they're counting by here because there's a 1, and here's 1/3, 2/3, 3/3, which is 1 right there. Okay, they had a computer go to every single point that was 1/3 away on like a grid of like 1/3 by 1/3, and they found the slope of it, and they just dropped all the slopes in there. Okay, so that's not going to be your job to make that thing. Computers make slope fields. All right, but all they're doing is taking all the slopes. If the curve goes through there, that's what it does. And the whole point of a slope field is this. It gives us a picture of what the curve would look like if it went through certain points. Okay, you can think of it kind of like a river current. Okay, like, do you ever, this is super weird, but if you drop like a ping pong ball in a river or any kind of swirling water, like at a carnival, like a game like that, if you drop something into it, like it's going to follow the current, right? It's get pushed all around. That's what a slope field does. Like if I were to drop a ping pong ball into the river of this slope field, it's going to follow these dashed lines, right? It doesn't have to hit them all. It just has to kind of go along with it. Like the slope field just kind of gives you like a basic I did. You see how they're all 0? They're all 0 on the x-axis. They're all flat. Okay? That's happening, by the way, because on the x-axis, every point has an x value that's 0. Like this point right here is 0, 2, 0, 1, 0, 1/3. If you put a 0 in for x, every single one of your derivatives becomes 0. If you follow the curves, though, it's going to come back up like this and then kind of flatten out like that. That's what it would look like if it started right here. That's all a slope field does. Okay? It's not crazy difficult. It just shows you what it looks like. So what they're going to do if they give you a slope field is like question A, is they'll say, hey, sketch the solution curves. That's what I just did, but they're starting at weird points. So that started 0, 2. So here's 0, 2. If you dropped a ping pong ball into that river, all the lines just go straight across horizontally. So we'll go this way, or we'll go this way, but you got to go left and right. Okay? That's the 0, 2 one. If you sketch from 1, 0, that's going to look like the one I just drew. Follow these lines. It just does this and curves. And down here, it just does this, and then kind of goes back up again. And look, they're not going to get like their ruler out and measure your answer. They're going to make sure that your slope curve follows it like that. So like if you kind of went down a little further than mine like this, and then came up some, and yours looked a little different, like that's fine. Okay, this isn't like a science. Again, computers are supposed to do this, but they just want to make sure you understand what that thing is. So that's what a slope field is. Keep practicing these free response questions. If you get done these and you got some extra time, if you look at 2017 or 2016, and you have any questions, drop them in that discussion board. Okay, I'm going to shut down this thing here.